Just gotta ignore it. Go to sleep.
Oh, I never thought of it. Let me try to listen to it. Very good.
Yeah, it's took me a minute, but basically. This poem is a person who was with their lover but had to leave to pursue adventure. Oh, but thoughts and cares for their person still remain on an adventure. That's so cute. That's great.
Oh, boy, yeah. Oh, God, yeah, I know. And also clings to my, I don't know. Honestly, I need to do them.
I don't want to do anything, but I think we did that.
Yeah, we don't either, be great.
I'm with you. I'm sorry for playing on the other side. I was so happy to announce like really is this.
Oh, I know, my computer just died.
You should do that. Listen.
It would be cool, but then we do.
Hold on.
Fail the script.
I'm gonna put that on.
I don't know.
That's what I'm gonna put that on.
Oh, me too. So, Patricia, what would we do if Patricia declines to come on some type of presentation and present?
Then just don't have that
What
one.
do you do? Banish her to the void.
Huh? What?
Banish her to the realm.
Then
The
if we
void.
just do exact on that topic, or we just-
In space.
you learn it individually.
Well, if she doesn't come, then it will have anything. So it means that she's not interested in.
Because her rotation is over, I don't want
Yes.
her rotation.
Our rotation is over on October 31st, and he will present after.
Oh, yeah. Yeah.
So, we can like attach these three things to Melody and these three things to Eva, but then it will be not even. Then Brad and Elsa will do for your. But let's keep it as a backup plan, but we will do it. So distribute between neighbors.
Or we all take one.
Yes, but if you present not in a sequence, then it will just crumble apart. Okay. What do you remember about last Wednesday?
Last Wednesday? Not much.
Me too. Do you remember anything?
Last Wednesday?
No.
Yeah.
Oh, no.
things were
Yeah, we had the figures.
Like two like this, and then they were like this as well, or
We
like.
talked about the really kind of probability distribution getting wider and narrower.
Yes.
We talked about.
Down.
We talked,
Oh,
we talked about the, like, what the graph represents, right? I guess more in a simplified term of like, to know the probability or the location or momentum greater than or equal to like 4 or 5.
okay. Can we connect what we discussed last time to this subject? Do we see anything? Patricia, I cannot express how happy I am to see you. And the whole class is happy to see you, because if you would not show up today and do their presentation, then someone else needs to take your subjects, which are quite complicated. There was a little coffee on the table there if you want to. It's the same code
Oh.
from now on until the end of the class.
Oh.
So I do not need to send anything.
We're just gonna be changing it.
Yes, yes. So, I think visualize any observable. Yes, partially we contributed to Fred's subject.
What? Which one?
Visualize any observable.
Yes.
So I think we partially did it last time. Well, we focused on expectation value of position and uncertainty of position, but it's partially covered.
Okay.
Uncertainty of position, yes, it was also covered. Computation of expectation values. Position, yes. Eva, you're lucky part of your task was presented last Wednesday. Or you're unlucky if you were not focusing on memorizing. Remember things that we did at the very end.
Of last class.
Based on your glance, it looks like no.
Well, was last class when Melody and I were a team? Or was that?
You're
last
always a team.
Yeah, but when I was coaching.
Yeah, when I was the champion.
Yes. Yes.
That last class.
Yes. Last lab.
Yeah.
Okay. And I think we also covered accumulation of expectation values into array. Do you remember this? So it is like AVGS equals AVGS AVG. So the array becomes longer and longer each time.
Yeah.
So it's also like part of your task. So your task is not super easy, but it looks like you are 50% ready. Maybe more, 60% ready. Let's look here. Size, normalization. We didn't cover it last time, but Patricia is getting an expert in normalization. She talked about it today in the class, right? Normalization, space and time. Those are quite relatively easy. And this initial condition is also easy. Alternative is hard. Modeling. Evolution from the term. Okay, so we covered less than 30%. So we need to cover about a half. Last time, I'm still very happy of our last meeting because we started bottom up, like from observables, and you got an impression that it works well and you can get something out of it. This meeting could be a little less entertaining than I suggest. Instead of instead of reading from backwards, we'll start reading the code from the beginning. And then if you cover things, well, basically I have two orders. One is just read the code and of the part of the code to the things. Or we go step by step of the questions and find how to illustrate it in the code. Maybe just moving line by line is more easier. Okay. I have no idea how they involve in the discussion. Like, whom and why to invite to the board, but it is my main task. So start telling the story and then find any opportunity to invite anyone to the board. Because otherwise it is so easy to forget.
Talking about the vibrational motion.
Did you hear the question?
Not in the second half.
It's about what vibrational motion.
Yes, like we could be about the frequency about all discussed the class, vibrational motion. Wow.
This code can be applied to like any observable.
And
So
A node include context nuclear vibrations. Does it answer your question? Okay, good. So right now, the parameters of the code are set up to describe electron in a free space. That it can be easily modified to describe in the box, particle passing through the barrier, harmonic oscillator, many other things. If one wants to apply it to vibrations instead of electron in free space, one needs to change math. So You may remember the numerical value for the mass of an electron, like 10 to the power minus. Huh? Kilograms.
30.
Sorry, I'm minus 3.
Okay. Okay. And you are ahead of me in this. But what there was only one thing that I remember about the ratio of masses between electron and proton. Hydrogen atom. What is it? How much heavier hydrogen atom is than an electron? Is it like, are they equal? Is it 10 times difference, 100 times difference, 1,000, 10,000? Huh? Just guess.
Between a hydrogen atom and a electron.
Yes. Or hydrogen atom, proton and atom. Okay, any other good an attempt to spread it? Any other
That's wrong.
I'm trying to put things positive. But ratio, absolute value set to other.
It was like about 10,000.
Okay, attempt is
About 6 degrees Celsius.
also attempt to spread your tool. Yes. Elsa and spread.
I got a plus like 0.1.
So the answer is in between. So between 100 and 10,000.
1,000. 1,000.
Much better. Now you are just 2 times.
500.
Or 10. Or 10.
2,000.
Yeah, 1,836. 2,000. So if one would put the, we will see where mass is programmed in the code, maybe in one of the first lines. If one replaces mass from 1 to 2,000, it will describe proton. If one 2,000 times 12, it will be which element is 12 times more heavier than hydrogen? You are studying well. You deserve to be in a graduate school. When in freshman times one defines moles, right? It uses like 12 grams of carbon, right? Me too. But there is carbon is used in definition of normal. By using mass of carbon, Avogadro number one defines moles. Like 12 grams of carbon is 1 mole of carbon. And the wrong, but it's something like that, right?
Yeah, it sounds familiar now you mention it.
Okay. So I was just answering the question. So let me share a screen on the other thing. Please open your MATLAB in the same code. And I think the most correct things will be just start reading from the beginning to our best. So first 2 lines I just it is melody notes preparing to save video, right? Correct? H bar equals 1, mass equals 1. So it is for electron. Maybe I don't know if this is a great idea, but maybe we should just keep going and adding comments. If the original comments are 4, we can keep adding them. So how can we justify mass of an electron being 1?
Really set it to whatever you want.
but our units of mass are not kilograms anymore, right? So we design a specific system of units where mass of electron is 1, right? And Planck constant is 1. What's the name of this? So this system of units is really good to describe like, atoms. What's the name of this system of units? If it is good for atoms. No, it is good to describe atoms. System of, yes, atomic system of units. Okay. And I do have this material in lecture 43 if you survive so long. I'll try. So Planck constant mass, what is NPTS? Just
Number points. Number ETS points.
yes, but I know it is not a fair game, but try to speak instead of me. What is points give you?
Your grid points, coordinates.
Okay,
So the size represents.
Time and space.
size of the box, right? So we can have absolute value of the size of the box in like meters or in atomic units or in angstroms, but we represent the space with certain number of grid points because we are not mathematicians, right? We don't have continuous variable. We represent variable with discrete points. Okay, what is P naught? Okay, why is not?
Initial.
Okay, good. What is X naught?
Initial position.
In which units? In which units?
Oh, I'm assuming it's gonna be in like. Well, in meters or like just nanometers.
Okay, scroll back. We design a system of units where H bar is
Oh, is it
one.
an atomic unit?
Yes, in atomic units. And so the one unit of length in atomic units is about half an atom. It is believed as a distance from proton to electron in Bohr's model. When if you believe that electron is revolving around a proton, and it is about the size of the s orbit, right? One atomic unit. What is X bar?
So with your initial.
Yes. Do we? Okay, I think we can be pretty quick in this. So
Number of times that the step is n.
okay. So what is and tau?
Now, well, I'm assuming time step is like how many, like every, like, the inner.
Take a minute.
Yeah, like how often you take them.
Okay, now about units, let's discuss it. So the atomic units of time, right? Typically, one deals with ultra fast measurements, one uses femtosecond, like second to the power minus 15, right? Or nanosecond 10 to the minus 9. Huh? Up to 10 to the minus
9 is now.
18, I think.
I'm sure I thought it was
10 to 10 minus 15.
pico is 12.
Go.
That's
Okay.
18. That's 18.
Atom. And if we have only UV visible at our disposal, we cannot tune pulses to be attosecond. But it's X-ray machine, like X-ray laser, something like that, to do attoseconds. But what is the? How does 0.1 in atomic units of time relates to a femtosecond? Relates to a femtosecond.
It's way bigger.
Or way smaller.
It's a tenth of that.
So I'm not inviting you right now to go into in check, but until the end of the course, we need to go to the VP and check details on that only units.
I just have the units chart pulled up.
Okay, so then it is not a term.
So that, the 0.1 is 0.1 of a femtosecond?
Oh, atomic units of time. And now we need to convert just in order to have an idea what we're doing. So in atomic units of time.
So,
One atomic unit of time equals to x femtosecond. So how many femtoseconds? So if atomic unit of time is smaller, then it should be 0 point something. How many?
0.064.
Okay. It's hard for me to remember. Let's do another one. Y atomic units of time equals 1 femtosecond. So how many atomic units of time we need to wait to be equal to 1 femtosecond? Just 1 divided by 0.024, which is we have a matlab right here. We can go into commands window. Huh? 41.67. Okay, 42 is okay. So, and this 0.1, it means 1 divided by 10 divided by 42. So it is this much of a femtosecond. So it's about 2.5 attoseconds. So Sam was quite close. Okay. These parameters can be skipped until we do boxes. So whoever else will do applications, and then we will return back to this parameter as well. Return and then dx size in atomic units, size between grid points. Okay. No distance. This and the nearest grid points. Well, it's just a formula. Nothing depends on size of the simulation. So, okay. This with number of lines changes because I add lines, but in on my screen is line 31. So, what is decay? It's not initials of meter given. It's something different. So I know something is written there, but how would you interpret for if you have if you present your talk and serve the term, you have visitors and speaker is asked by attendees, what is the meaning of decay variable? What do you answer? Huh? So 2 pi divided by L, or L is size of the box. Just guess.
I don't.
So, let me what to say, suggest your directions of your train of thoughts to the part in the right direction. So we can miss technical details, but at least we will have right direction. So, in which circumstances during the last 2/3 of the class you have seen 1 over size of the box, or 2 pi, or pi divided by size of the box. Pi over L is appearing. Let me take here as an example. Sine of x equals square root of 1 over L times sine of n by x divided by L. Does this tell you anything? Okay, let's focus more not on the normalization, but this. Right. So, in which circumstances you have seen this combination of symbols? So, our class is 1,000 methods and 3 applications. In which of the 3 applications you have seen? Have you seen it in harmonic oscillator?
No.
Have you seen it in free
No.
electron space?
No.
Then which of 3? Is it energy or wave function? Okay, so I apologize. And now, what is the let me reshuffle it this way. Pi divided by L and then multiply by x. I have an idea what to say, but I really want you guys to give a little ideas.
I know we've seen it.
Okay, so let's return to the thing about. Consider 2 waves. Quantum waves or just waves in the pool, where we had a hypothetical pool party with sun.
Yeah.
Right. So which wave has higher momentum? The one with frequent fringes or one with shallow fringes?
Higher what?
Fringes.
No, what, wait, so it's, what is the
Oscillating quicker or oscillating more like
Bigger radius.
huh?
Bigger, like the longer it is, it's essentially.
Oh, which is taller?
3.3. High or lower.
Moment in space. Like suppose but different momentum. Like suppose I do have a modern camera, which maybe that's rules. We all have cell phones. And then I observe waves on the surface of a lake, or maybe I put a cup of coffee on my washer and dryer, and I make a screenshot and I see there are 2 waves. One goes with very big period, each hump is very far from each other, and another has very dense fringes. And then can I, based on this information, decide which wave will cross the lake quickly? Slow wave or which is faster? With lower or higher fringes? Yes. Especially for elephants, different systems make a crazy dispersion relation, but for elephants for sure. So higher ranges corresponds to quicker wave. Everyone agrees? So kindergarten mission accomplished. Now, if we have higher value, bigger n, or higher value of this stuff divided by L, what does it correspond to? The higher this highlighted thing, the bigger, the faster is the wave. And the faster the wave, it means it corresponds to high moment. Okay. Okay, your train has departed in the right direction. We will need to speak about momentum. and the momentum will be represented, momentum distribution will be also in the discrete space. So same as in the Cartesian position space, we have dx distances between nearest neighbors. In the position space, dk will be distance between nearest points in the momentum space. Okay. So we can reformulate it as distance between the points in momentum space. Okay. So x number of points, each of which offset by dx. So it will be just a line or vector corresponding to all grid points, like an argument for a function, right? Agree? K from 1 to n points times dk, it will be like argument if we want to work in the momentum space. This is for delta. You have there are a lot of things for delta. Yeah. About half of the code. Yes, whatever. We will cover your things next meeting. Now you're just welcome guests to relax and accumulate any shit. Right. This thing we need to reset 0 point in momentum space to include both positive and negative values of momentum. Okay, this equation in the line 72 is extremely important. I'm going to stop sharing here and start sharing on the other facility. So I don't know, should I be happy or unhappy, but the most important subjects are covered not by a graded member of the class, but a graded student visitor. But I think this little arrow is what we're going to study in the line 71 that we focused. So you can feel yourself safe that Patricia will hopefully take care of presenting it. But when you will be presenting the next round of finals, which we always for, there is a high chance that each of you can be asked. Not by myself. I will be even protecting you in front of people, but sometimes they may have sharp. Maybe even sharper.
Oh, that's scary.
So I feel like you are a sports team, and I feel myself more like a coach for you to overcome this judges. Okay, so right now we will focus on initial conditions. So soon it will be presented by Patricia, if she doesn't decline her. If she declines, then probably it will be assigned tomorrow. Okay, going back to screen this matlab. So you see this line is longer than the size of the screen. I'm going to look on it and write down the this equation, this programmed formula as a mathematical equation in the blackboard. And probably we don't need to remember it in the middle of the night as a framework, but we need to be able to recognize each portion. So we'll practice the principle of tension problems, divide and conquer. So we need to divide this long line onto parts and conquer each of them to explain what each of them mean. Make sense? So I am going to
So maybe code and here math. So we start from SQRT dx. The next term is x I p naught x minus x naught h bar. Next one. X minus x naught point squared divided by 4xy. 4xy. Times, so it's still the same line. Divide by 2 pi x bar to the power 1/4. Okay, now we need to learn how to read backwards. Do you have? Yeah, I'm probably do it myself, although I feel everyone from the class would be able to convert into math equations. I just want to save your right to the board. When I feel with something more complicated, I will ask you guys to come. So, Patricia, will you recognize what this one is? Is something
Can I go closer? I can see something.
you cannot? Okay, let me convert each term into the math equation, then you try to interpret.
Okay.
So square root of dx e to the power I p 0 times x minus x naught e to the power minus x minus x naught squared divided by 4 sigma x bar. And here power 1/4 1 divided by 2 pi sigma.
It's like the normalization.
Yes, you deserve to be in graduate school. Normalization. Yes, and now you know why it is needed to have probability, integrated probability for this one. We have 3 more terms. Let's refocus on the class. So the second one.
Is it?
You can read it out loud, but I bring you comfortable to see what it
I can see it. It's e to the power of I p naught times x minus x naught. Is it supposed to be divided by h bar times something?
Yes. But h bar equals 1.
Oh, okay.
So what do you promise to number in zero?
Play my head.
Yes, correct.
Yeah.
Okay, so this thing includes plane wave as a factor. And in plane wave, it imaginary, it oscillates and it has momentum. The higher the momentum, the quicker the fringes, the quicker it goes through. Okay,
No. It's a feedback because there's a speaker right there. Let me interview Sam. Simulation.
So, like,
You play-
is it my-
Yeah.
I have it.
How many computer game players do you take against you? Alone against how many computer players? Okay. What is easier to have more or less computer players against you?
What? I think it's harder for them to know.
More is easier because they fight each other and you do
It depends. I think it depends on the math and laws. Like this. But if you get Gandhi, then there's this judge for like 50 or 3 times more peaceful than just the max aggression. And you can say it one. It's super funny.
Okay, so you don't need to hide it.
What? Oh, that was.
So, what's in the line number 3?
I see an E. Are we looking on the left or the right side?
Right.
That is- there's an exponent. Oh, that was good. I see final position minus initial spread all over. Is that 4 sigma?
Okay, and just try to interpret what is this.
Well, it's you're squaring your change in distance, and I'm completely blanking on what sigma stands for. So I'm just-
It's just a bit parameter, but have you seen this equation ever before in your life or in the course?
I feel like the answer is supposed to be yes, but I can't remember just thinking that maybe that on the day that I was gone.
No, you were in the class.
I don't know then. I feel bad.
It looks similar to part of the density of states.
Okay, it's an interesting connection. Yes, density of states includes, but we started this function when we were studying the electron in the free space,
Okay.
and I was trying to bring printed money to the class or show.
Oh, is that supposed to be like the distribution like curve? So it's your distribution, like your probability of like rotation of your particle.
Mhm.
Is that the entirety of it?
Yes.
Yay!
So, did everyone hear the teaching from Sam?
Yeah. Call me Professor Steve.
Yeah.
So, do you want to criticize anything for this professor?
Buster Stevens? No,
Can you repeat what?
not really. I kind of missed them. Samuel, can you please repeat yourself? I missed like one bit.
At least they admit it.
Please
It is.
your information.
It's the probability curve on the German number, so it's the probability of where your particle is.
Gaussian curve where the particle is over time.
Everyone agrees?
Yeah.
Okay, perfect. And the last one, Patricia told us normalization. This one is probability distribution. Yes.
That's amazing.
Yeah, probably. I will refocus camera on the board rather than drinking Steven. Not Steven,
Yeah.
Sam.
I'm in your research lab.
We got some first names.
I just switched first and last.
It's okay.
Thank you.
My grandma calls me my coach name all the time, but she also has
Wait,
it becomes very difficult for like grandchildren, grandparents when there is like 100 of them and then listing all possible names. Okay, so Patricia told that this is normalization. Sam told this is position of the particle, right? And you see, Vx naught programmed in here tells us where particle is initially, right? Agree? And Elsa told that this is a plane wave, and P naught tells how for momentum, tells how quickly it goes, right? Although at the very first meeting of this class, Sam taught us that position and momentum can be measured simultaneously. But we're not measuring, we're just setting them up. No, not observing. We are setting up a wave packet with a specific initial position and specific initial momentum. Wave packet. Yes, yes, this is an equation for initial wave packet. Okay, and what is square root of dx? Why it is needed? This is a tough question. I was not able to answer it for a long time, even while writing this code. But without it, it's something. Normalization is not possible without this dx. So when we want to make absolute value squared of the wave function, psi squared, and want to integrate dx, we will represent it as a summation, sum of p of psi squared, and we will not have dx. Like we need to make a transition between the summation to integration. Therefore, we need to plug to remove to. I don't have the right word. Port transfer this increment of position from integral to this summation. And since we typically take the psi in the squared in the second power, then we need to preliminary take square root of dx. Then after, when we take square, everything will integrate to 1. I'm not sure that even sharp tooth visitors will be able to formulate this question, but you will be ready just in case. Some of the visitors will be former students who took this class and know this.
No.
Are you inviting like previous year's students?
I'm sending like invitation to about 100 people.
Oh.
Maybe only 5 of them will agree to come, but it should be a big celebration.
Party.
A party, yes, yes, wave packet party.
Big packet party. You gotta bring like, so people bring cookies to their defenses. Yeah. Can I ask a question? Fine, that's fine. When?
If your instructor doesn't eat this cookies, then it is not a break. It is just social. So you need just to put a cage around me so that I can attach to.
Cookies, not for Dimitri. What was that?
Well, to avoid bribery.
The probability distribution is. Are we talking about probability distribution where is it in particles of box or is it like where? Because in class today, when we talked about the probability distribution, it was entirely another question. Do you understand?
Yes.
So this probability distribution is necessary.
Perfect question. I will not go forward before I see the whole class understand the question.
All out? You read it on board?
Yeah, I'm just missing an alpha, some alpha. But I'm missing it. I don't have it here. So yes, yeah, alcohol free campus.
Okay.
Although I'm missing, I'm not going to violate anything. Right? And I even had, yeah, I put disclaimer, never drink Irish coffee on campus. So, did you got the question from PhD candidate Patricia?
No, I missed the question.
You ask her to reformulate.
Can you please repeat your question?
I said, my question was, the equation for the probability distribution, I was asking which, is the, application that is being used, because the one we talked about today for harmonic oscillator, the probability distribution equation is quite different.
Okay.
So I just want to know in which medium is this probability distribution used?
Yeah.
Great question.
No, the answer to your question.
Yeah, but it's a good question.
I understand what you are asking.
Okay, now I'm going to answer after a little review. Okay, so right now, there are several answers to this single question. First, what we are setting up by this C naught is not an eigenstate. In class, we consider eigenstate, which will not change over time. Those of you who are experts in differential equations, and all of you as at initial class, you know that we solve when we need to predict future, we need to start from some initial condition for the function. This is initial condition that will propagate forward, right? So it is not an eigenstate, it is just initial condition which will change over time. It was answer number one. And we didn't, literally didn't answer the question. Now, which media are they formulated, or which application? Our class is 1,000 models and 3 applications. Which of these applications this wavefunction stands for? All of them, each of them, and even more. So this setup is universal, and one can study Gaussian wave packets in any potential, either electron in free space, electron in a box, proton connected to another proton, like hydrogen H2 molecule vibrations, and many other things. So it is a universal setup that you use very broadly. Did I answer your question? Let's quickly look on the list of questions and make sure that we are on a good track. So we are done with initial condition is chosen as Gaussian. So it is not all things that Patricia will present, and each presentation is expected to be 5 minutes. It's very hard to squeeze all information in 5 minutes, but at least 1 minute or 50 seconds of our presentation is secure. Okay. So I suggest we just keep going through the code as it is written, and then make connection to the questions. Okay. There are several boring things that can be forgotten right after you pass the midterm, but I think it is my duty to present them. I think I can erase this thing and keep writing there. Is it okay to erase? You don't see any big wisdom in this writings.
You may erase.
Thank you so much. I'm looking for a reason.
Dimitri, what are the 3 applications? I always forget what they are.
Particle in a box, particle in a box, particle in free space, and the harmonic oscillator.
Okay, erasing. P not equals
FT T naught. What is FFT? Melody plus one.
Yeah.
What, M plus one. Why it is double F
Fast.
plus one to everyone?
So, under it.
Well, I could have done it. Not fast, but.
I'm always forgetting that I'm talking to intellectual elite of the book. I just trying to make up my mind to make this class accessible to kindergarten kids who are illiterate. So what is an equation for Fourier transform? So sine of x times e minus I p x. If you have h bar, or if you don't have h bar, you can put k d x integral sine of k. Something, something. I think it's time of error.
Can't wait.
Just tell something about what you see and what have you seen earlier in the class.
Oh, no.
Okay, let me help everyone to depart or switch. Yes. So which homeworks do you remember? Which homeworks do you remember? There were not too many, like half dozen. First one was a garbage. We don't need to remember.
Most recent one is. That's what I'm. Yeah.
Did we ever practice Fourier transform in this class?
Yeah, well, we explained what it was. I don't remember doing it, but I remember explaining what it was. Oh, man. No, I don't have, oh, here we go. The technique of converting signals between domains.
Okay.
Yeah,
And can
I
you open your folder?
yes,
Either this image.
this is.
Which one?
Yes, so- what this image is?
That's a Gaussian.
Okay. Okay, yeah, it's really quick. So Brad did help me, but she didn't help
What?
me.
Were you not looking at homework?
Yeah, I was.
What number?
I don't have it written down. It's not homework 3 though. I can tell you that.
Let me try to recycle and yeah, you're looking in the right. So we were studying like I will doing open cups. Otherwise it would be too long to do puzzles. So when we were studying an element in the free space, we did formulate a question: what would happen to the bits of the wavepacket? Do you remember? Yeah. What happens to the bits of the wavepacket?
What?
Oh, it increased.
I don't know.
Yes. Right?
Okay.
You remember?
Why?
Yeah.
This is the uncertainty.
The height crunches down
Yeah.
and the width increases, right?
So how did you prove it mathematically? With these groups? It wasn't easy. We suffered a lot of mathematical procedures. Let me,
I don't remember the exact process, but the uncertainty of its position grows as time goes on, right?
yeah,
That
a square thing.
Okay, yeah.
Okay, let me try to remember what I can.
Yeah.
Without cheat sheets. How do we predict future? So psi xt of the future can be, there are three ways, right? And one of them is expansion coefficient. Doesn't ring the bell. Okay. And what's the like eigenfunction, eigenenergy, and expansion coefficient? It sounds like I'm sitting in the deep well, or someone is trying to make me suffocating under the pillow. So, and C sub m is integral phi sub m of x times psi of x t equals 0 dx. Right? So instead of if we had a plane wave, I see by the word of plane wave, you guys right. So if it was a free space, then phi is a plane wave, right? Then it is E phi x, and then this C expansion coefficient will depend on P. And here we replace summation with integration. P, C, P, and here we replace this with E minus I kx. Here integral over k, here is integral over x. Sorry for my orthography. So we do Fourier transform once to go from initial wavepacket to expansion coefficients. And the second time, when we go from expansion coefficients to the future wave function. Just say yes, we remember. If you would not select projects, it will be one of the exam questions with some derivation. So, I cannot wait until someone votes for the exam. So, what is phi naught? So we convert wavepacket from Cartesian space of position into space of momentum. Okay. So it is literally this psi of k. Right? So it is a wave packet represented in momentum space. Thank you. Please share. We still have time. There are a couple of boring and hard things, but just prepare. They're not the hardest part of the class. Just prepare to. It will be much more funny very soon. Maybe just as a little, I cannot call it break, but as a little ongoing entertainment. Let's look back. On this thing, like candle or whatever you call it. Right? Yeah. Thermal candle. I cannot find the best way to represent it. Should we go in different ways? So now X goes in the opposite direction, but originally it is localized wavepacket, and as time passes by, it becomes broader and broader, and the expectation value moves. So this initial value is what is programmed with sign-off. And the goal of the code, as it is set up now, is to predict psi as function of t. So just to bring a little bit of life into this boring abstract concepts. So it's very short writing, but there are deep ideas in any two you. So what do we remember about operators? Like, how does momentum operator look like? What do you remember about momentum operator?
Chart.
Yes, from the postulate.
The operator tells you what mathematical functions.
Yes. So which mathematical operator corresponds to operator of momentum?
Oh, I don't know.
I can look at everyone just to stimulate thinking. So
I'm thinking, I'm trying.
Is this?
it's perfect. I'm just I wouldn't say offended. I'm surprised that you look for this information elsewhere, not in my lecture notes. But yes, correct. So please teach all this. Mathematical operation corresponds to momentum operator. Just read what you should.
It has negative I, H R, and derivative from partial derivative with respect to X.
Okay, perfect. So, what? Which mathematical operation corresponds to momentum?
Negative I and H bar and the partial derivative of X.
Yeah, you can skip constant. So derivative, right?
Yeah.
Isn't it surprising?
Is it?
Everything.
Yeah.
Or it is?
Which mathematical operation corresponds to momentum? Which mathematical operation corresponds to momentum operator? Just repeat after else and for blame and the president to say.
I was on here, so I hope that the past thing. And that's.
That's okay. So, just formulate your question to Fred and Elsa. If they didn't explain well.
Fred, what did you just say about momentum operator?
Oh, well, it depends on the partial derivative of X.
It depends on the partial derivative of X.
That's cool. Did you just repeat it verbally, or you penetrate by your thought in the deepness of this idea?
Do you want the honest answer or the answer that you want?
So I give you a like little time interval to do the second part, even if you didn't start it. So typically momentum in classical mechanics deals with like velocity,
But, yeah,
derivative of position over time.
Yep.
Right? And here it's opposite, it's derivative over space.
okay.
Isn't it surprising?
No,
No,
that kind of makes sense.
I'm going to learn sense.
So you say that typically, momentum is like distance over time, right? Like, and so distance over space would basically be the same thing. If you're doing like your distance over the space travel, would be the same thing. Now you got that. So distance over time gives you momentum. Distance over space.
You see how confusing it sounds?
It does, but I mean, it makes sense in my mind.
Well, it makes sense because you are, well, my goal is to convert all of you to the quantum wave thinking.
When you say space, what do you mean? I guess.
Just position.
So it's just literally position over position. Is what you're saying.
Then if you do one.
Yeah, but that's basically what you just said is that your position is your distance.
Yes,
You're
so
contradicting yourself.
let's argue who is contradicting the whom.
Distance implies that you're somewhere else in relation to a specified point. Position is just where you are.
Okay, but what is wrong in the train of thoughts provided by Sam? Did anyone can catch something that either wrong on your point of view or what you think will be wrong from my point of view, even if you are on Sam's side? Why I am so skeptical of Sam?
Because I'm tall.
So maybe they didn't hear. So explain why you think that. No.
Nope. I said it once, I'm not gonna repeat this.
That's not how it is. How to
It's
answer
clear enough
momentum.
because I realized why I'm.
But just give them a chance to say it.
I don't know if it's gonna be exactly what I said, but I said it kind of makes sense because distance over time is momentum and distance over space is like the space travel, it's like distance over the space travel. But then I realized that you just don't have a time frame, which is why I was, yeah. So there is no time frame in which you can relate it to. So yeah, you're right, it's a bit shocking.
Okay, so things are falling down because we have the intellectual strength of this class is high. It's like telekinesis, things are falling down. When originally, before now Sam did repent his original idea. But when he was thinking very sharply and clearly, the only thing I didn't like in his original thought, that his mindset is yet in the classical mechanics. When we have a certain position and momentum and the material point is traveling through space, right? When we want to change our mind to quantum mindset, we do not have particle with a certain position and momentum. Although we can do some tricks with it, we have a distributed wave function, right? So I'm going to draw something on the other board. And it will be a repetition of the thing that we come back again and again. But it's not possible to memorize it. It needs an internal conversion to start thinking of this language. So we do not, like, if you have just
position as a function of time in classical mechanics. Then we do dx over dt, it will be velocity, and if we multiply it by mass, then it will be momentum. So derivative over time. So classical. Classical not as like traditional, but versus quantum. Quantum. Here we do not know we have only wave function. Right? And then we define operator of momentum we have as a ddx applied. We think that it is applied to the wave function. Okay? And now here is the logic. If we assume that wave function can be proportional to E minus IPX over H bar, right? Then if we plug it into there, dx E minus IPX over H bar will be equal what? Minus IP over H bar, right? And we put here a factor minus I H bar, which will cancel here, I, and then it will go to the value of momentum. And it's surprising and shocking, but I see you are moving toward this mindset. So you guys taught me about 40 minutes ago. The denser the fringes of a wave, the quicker it goes, the higher the momentum. So this factor tells how dense the fringes are, right? And the derivative brings this density of fringes, this P, from exponential to outside. You get it? Yes, yes.
The waves with a higher frequency move faster than waves with a lower frequency.
Okay, go ahead.
Because if they're moving with a higher frequency.
Mhm.
If they're moving with a higher frequency, but like this one is moving with like a lower frequency, they can still travel at the same speed. There's just more waves for the one with a higher frequency. And so it's creating more waves in the same amount of time that this one is creating one wave, but they're moving horizontally at the same speed. And so I don't think I'm understanding how this one is moving.
I think it comes down to, because I'm assuming.
Or is it just the fact, is it just the fact that it's moving faster?
I was gonna say, I think it comes down to like, if you think about like the wave as the particle is like complex, right? It's not moving as a particle, but as a wavelength. The higher wavelength can be treated as if like your change in energy is happening a lot quicker than like, slower. It's like that's kind of how I guess would get it.
So it doesn't change the distance that it doesn't have anything to do with the distance that it's traveling, just that it's moving faster or slower.
The momentum, so it's moving
Yes.
faster.
Okay,
So that you don't
So
have.
maybe if they're moving the same way, but this one's moving faster, so the momentum's higher.
okay, yeah, that makes sense then.
Is that correct?
I like how you explain.
Okay.
Not me? Okay.
Momentum.
Oh, Sam, you were digital designer. A father of this discussion.
I'll take it. I'm a founding father.
Okay, and yeah, that does make sense, because then it's in relation to literally just how fast it's moving, not the distance that it's traveling in a certain amount of time. I think I get it now.
I'm so happy.
Thanks.
In some sense, this discussion fulfills the goals of the course. Of course, we will need to complete the program, go to
Course, it's done.
to like 1,000 methods and several applications and presentations, but this discussion fulfills the core idea of the course. And the equation, this equation is the only thing that cannot be derived from anything else. It needs to be like set up. It's on the maybe the only equation that one needs to memorize. All other things can be derived from it. Whew. How does it relate to PO? Oh, okay. I'm delaying myself, but the code that we are looking at is based on implementing momentum operator, Hamiltonian, and evolution operator. And those will be key portions. I can skip this couple of equations because they are more auxiliary. I can just give a brief comment that very soon, definitely today, in like few minutes or in 5-10 minutes, we will describe the representation of momentum operator in a matrix form. In a matrix form in Cartesian space. I see we are already bored. I know how to make it board. Sure. The derivative operator in discrete form looks at least as a three-diagonal matrix. Non-diagonal, three-diagonal. But if we describe an operator in its native representation, like momentum operator in momentum space, it will be diagonal. If you look for position operator in position space, it will be diagonal. If you look any powers of position, like V or potential as function of X in X space, it will be also diagonal. And those two little things, so it is momentum operator in the momentum space, and here is position operator in position space. And here are the reference points. They will be useless in everything except free space. So you can just flip for another 30 seconds or 3 minutes. So it is a Hamiltonian of momentum operator in momentum space when there is no potential. And then evolution operator will include this Hamiltonian times delta t, and it will be missing the potential. So it works only for free space. So this portion is useless and unique. It is only academic for particle in free space. Now, when we go next, we are coming to much more recent things. Yeah, you will learn about children. Whoever is responsible for visualization.
Oh man, I think that's me.
Okay, you'll find about children.
You'll fight about children?
Huh?
We'll find out. Find out about the fight.
I could fight virtually.
So,
They keep piling up, yeah.
At one time, or one after
If
another.
they come at me like,
Find out if it's enough of a tiny spider, one giant big spider.
How many 6-year-olds did you take on before?
My partner asked not to know.
I could probably take 250.
No,
Yeah, you don't do
no,
it.
can't.
And then you just start taking.
There's
No,
no way. you can
no.
tell.
Big here and I had 15 kids and. No, no, no.
school district too.
Back
Like
to.
200 kids in the summer, I know.
oh, okay, Elsa joined the club. I can ask Billboard not only to Melody, but also to Elsa. Elsa wants to say something?
The back to the subject club.
No. What do you mean, no?
And leave this
Yes.
class. Yeah. Just see yourself out.
I especially like, and I even shared to my colleagues some of our discussion with, like, I do not set anyone up, just telling us as a joke without names. I thought, like, even with hard tasks and grading, I hope we will stay friends. And then everyone else, and Frankel, speak for yourself. And my colleague, I didn't disclose the name, but my colleagues like this comment a lot. Like, be careful with that.
They got a kick out.
Okay, so lines 117, 118, 119 are most important lines of the code. So if you cover them, they will be like minimal task for the day will be done. So there could be a little more comments after this, but it's my primary task to cover this equation. So maybe I will skip these things, explain what are these two equations are, and then return to missing parts. So, do I have a permission to erase this stuff? Thank you so much. That's okay. Excellent. I'm just refocusing. Focusing. Focusing is done. So erasing. So line 117, ham is not food. Dx times dx divide 2 times mass close brackets plus diag of b semicolon, and then line 119 g tau 2 equals expl minus I star tau divided h bar brackets times CHEM2. Stop sharing, just begin. So H P x times px. So what does subscript x stand for? Subscript x. So it's momentum in position representation. Divided by 2m, by 2 masses. Plus just potential as function of x. Right now, if you carefully scroll through the code, potential will be defined as 0 everywhere. But later on, for our projects and for presentations by Elsa, potentials will be set up to represent different models, like box, oscillator, and stuff. But CHEM2 is Hamiltonian computed by methods number 2. Okay, clear enough. So let's convert from backwards from coding into equations for g tau 2. So I would immediately use the letter U and tell it like exponential minus I h2 divided by h bar times delta t, or we can, instead of delta t, we can use tau. So do you remember what is this? Yes. So 3 times you truly deserve to be impressed. I don't know how to the question and how to make the challenge. But also, two columns, error, two columns,
We've all given some of the comments.
let's go to the second column.
I think it's Fred's turn.
There's nothing so much. Anything.
I don't know, I mean, that's the evolution operator, you know, for predicting the future.
Okay.
You know,
So what do we do with evolution operator?
you,
Store it in the fridge or?
you could, I guess you could do that, but you would apply it to like a wave function.
Yes. Yes, everyone, okay. F plus one.
Yeah, you get more than F plus.
Oh, I didn't notice before.
Okay. Joel will be credited. Oh, I like the sound. Bigger transmission is going. So, red gives us teaching, so that if you apply U psi at time t, you will get psi at t plus delta t, instead of placing it in the solution. Correct? Okay, so I have a dual task. First, and most important, to identify if our code has this most important line, if it is programmed, if the equation is programmed. And then after hopefully we identify this line, I will try back and go back to how PX operator is programmed. It looks like only one symbol, but it is the biggest challenge for the whole code. And it will be main task of melody. Okay, so PX commutations and program just to program PX operator will be interesting and challenging. No, not yet.
Pretty sure what kind of snacks do you like?
What?
What kind of snacks do you like?
Food.
He knows what snacks.
I need to be in the iron cage so that no one can accuse your bribery. So the brain is done. I'm just finding it over. I will have an announcement that you may like, but it will be right now is a very free nature to say about what I'm going to say. Just to inspire me. Our goals are to complete tasks of the class, do projects and stay friends, right? But on the top of this, if you are really curious and, let's say, diligent, motivated for success and going to higher orbits of this, if the following will be approved by your current researcher, right? So it's very easy. If your mini research project will be absolutely outstanding, then there is a chance to formulate an abstract based on your project, submit it to a conference, and celebrate success of this class on the mission forward. but it's very easy. And then we can treat each other with
Yeah,
very
and then
dignity.
you can best friends.
Right.
instead of-
But it's not a promise, it's just light at the end of tunnel. Like very, very easy, but
Something that you can strive for, yeah, you pronounce this, I heard. That line, notice that. It's dark.
so 179 psi 2 equals G tau 2 times psi 2. I know my calligraphy is very below standards. So what does it mean? I think Fred already, if someone explains it later, it is retroactive. And Fred explained it forward before they arrived. So what does line means and stands for? Fred already talked. Your watch is over.
And also, you said it. What it is.
Oh, if you need to go, your last word.
This is your check it out.
What are we?
Why?
That alluded to you applied it.
To what? Is there anything that surprises, irritates, challenges you in this little line? Is there any logical paradox?
I choose on both
Side
sides.
two is on side.
Yes, exactly. Yeah, thank you. If you need to go, it's fine. You cover the main part.
Okay.
It's better if you don't stay, but even the emergency. So, don't you agree that it is a paradox? Right?
Yes.
So, it is a paradox for any.
Doesn't that mean that how two has to be full?
So, first time I was respectfully criticizing Sam for his mindset is even classical.
I'm sorry.
It's just so surprising for Sam. So first I was respectfully criticizing Sam for his mindset was in the classical mechanics, classical physics. Now his CPU mental processor is truly strong. So it is not his duty if it does something not what I expect. It's because he found he set a foundation for his train of thought from the I would say wrong, but inappropriate ground for this class. So it's frankly criticism. You're not punished for anything. So first he grounded his conclusions on the classical mechanics. Now, when he told like, don't G tau 2 should be equals 1. It's not wrong, but he grounds his thoughts on the mathematical style of thinking, which is not wrong. But here we are in the lab, not in the class. In the class we can be mathematicians, but now we are programmers, and it is program style of thinking of Linux gurus, of professional programmers, right? And in programming, I'm symbolizing how a person is typing, not as a. Oh, okay. I do not want to symbolize a huge spider. Okay. The writing like psi equals G tau times psi. Ciao, bambino. Wow. So, let me type it right here because there is no space in on the board. So it means it should be interpreted the following way. So psi 2 at t plus tau. So next step is forwarded from psi 2 at t by multiplying of g tau t. So sign equals is not in a mathematical sense. Here, sign equals comes from programming sense. So it is, let me create another line and it means assign new value stored in the variable psi 2 based on just a second, based on the result of operation of this evolution operator operation. Yes, Melody.
So, if I'm understanding this right, so in the code, originally psi 2 is assigned a value, and when it's executing the code, it's thinks of it as that original function, and then when it gets to this line, it replaces that value with new values based off of the operator g tau 2.
So perfect. I cannot do it better. So let me try to make an illustration, although you did everything correctly. I think we have copies of this code from previous year because it was put in here. Yeah, you can check it later. I think it is just printed version of the same code. But I wanted to do a little silly demonstration. So camera will be. I'll take some time to place. So, right. So here's the wave function psi 2. Okay. Now I have a program. I do have a little drawers in the memory of my computer. And I store wave functions in the drawer of my computer. Just right. Now I take it, perform an operation, and then place it back. So here's a mindset of a program. So it doesn't mean equal mathematically. It means take, perform an operation, and put back. Okay?
Because every time you have an equal sign, it's basically assigning a variable, right?
Yes, it is an operation of assignment rather than declaration of equality.
Or just like changing.
Yeah. Okay.
That was great. That honestly, that was a good.
And too bad Sam lost me before he could hear that. Now he still thinks it's one. Gosh.
I'm not helping them shoot.
Okay. So I have planned to finish in 10 minutes, but we follow the schedule, and there are a few little things to round up this part. So I didn't expect to go over each line of the code, but most important things. So this is to be noticed, and I think Sam, he goes over principles of wavepacket propagation should explain it. So he's mandated to watch the recordings and learn how to tier this paper. And Patricia, she also will, it is part of your presentation. there is a little thing that you may notice, may not. So, what about line 171? How do you interpret it?
That's the
So,
most important part.
is it written somewhere?
Why first?
Most important part, okay. So most important part is everything after this line, but, as I think it's time to do a second round of comments.
Oh, wait, that's you. I'm supposed to tell you what that one means?
Yes,
Well, it's just to repeat it once, isn't it?
how many
I
times?
know, once. Oh, right. From one to the value of n out.
How many times? If n tau is a like natural number or something, how many times this will be?
79. It's from 1 to 7.
Correct, correct.
Okay.
So we are, imagine myself tearing this piece of paper 699 times.
That's a lot of times.
But you get an idea of it.
Yeah, it's like re-inputting the code, removing, editing, and inputting the code back in for every single trial.
So wave, absolutely correct. So wave function is updated 699 times.
Yeah.
And then we can predict future 699 times. 699 images of future.
Yes.
Everyone agrees with those?
Yes.
Okay. So,
Yeah, yes, Madam President, actually, thank you very much.
those two lines, 179 and 171, are most important practical things to explain how the code is working. And even if it is not your task to do it on midterm 3, be ready to answer these questions on the final presentation. I can promise that based on previous year's experience, there will be questions from audience. And you can impress them by tearing paper or maybe finding something different way to explain. Okay, so let's scroll back where the GTAL is declared. GTAL.
Yeah, what?
And in the remaining 5 minutes, I need to do something really hard and challenging, and it will be on shoulders of Patricia for presenting. Not yet. Not yet. So, in order, Patricia and Melody. So, in order to program GTAL, we need to program HAM. HAM2. In order to program HAM2, we need to program variable PX. And you know, PX is derivative, right?
Yes.
Now, I do not see any derivative in here. So this is a crazy thing that explains how to program momentum operator. And I'm going to erase everything on that little board and just mumble something as much as I can in 5 minutes. And then we probably will return back to it when we meet next time and when we squeeze the rest of the background of the school before the presentation. So,
Yes. Right there.
so I will hope that you remember this, that you already remember this equation, right?
Yeah.
Momentum is a derivative. And we need to program it.
Momentum operator, that's what I remember in the name.
Okay. I'm scared. I have fear. So, definition of derivative in your calculus one. So dx, let's put it just regular, of psi of x is psi of x plus delta x minus psi of x divided by delta x. But in the limit, delta x goes to 0. Right?
Yeah.
Now, suppose we do have x1 plus delta x, x1 plus 2 delta x, x1 plus 3 delta x. So it is our grid points. Grid points. Agree. Grid point. Okay. Now, suppose we do have a wave function psi of x1, psi of x1 plus delta x, psi of x1 plus 2 delta x, and so forth. And keep going. So vector, state vector, wave function. Now we need to design an operator that will act and change this wave function in the same way as momentum operator. So we need to design a derivative. Design a derivative. So here is the expected answer. So here I need to get psi x1 plus delta x minus psi of x1 divided by delta x. Here I need to get an element psi of x1 plus 2 delta x minus psi of x1 plus 1 delta x divided by delta x. Here I should get psi x plus 2 plus 3 delta x minus psi of x1 plus 2 delta x divided by delta x, and so forth. Do you understand? Yes?
You carry the twos and the threes into the bottom, like the delta x on the bottom of the equation. So when you have psi of x1 plus 2 delta x minus psi of x1 plus delta x, what if you have that all over 2 delta x?
I can put delta x out of brackets, but not the 2 and 3 and 1. This will be running. This will be always different.
Okay.
The 2 minutes left if you want to be rigorous. So I can put 1 over delta x out of bracket. This is possible, but these things cannot be put out of bracket because, for example, if you take derivative of x squared, the answer is 2x. So at each point of x, the answer is different. So it is not, unless you take derivative of x in all other derivatives, it will be different in each point, right? So we cannot pull it out of bracket. Now, we need to design such methods by acting of which on this vector, we will get this vector. Now I'm not scared. So we will run a few minutes over, but not much. Yeah, thank you. I'm looking for any other color. Okay, that's fine. So here is the matrix consisting of rows and columns. And by multiplying this rows by this column, we need to get this column. Okay? Not a surprise. It agrees with your fundamental education. Now, we need to, for this first element, we need to combine this one and this one with factor 1, another with -1, right? And we will need to, and the delta 1 over delta x can be outside of the brackets. Delta x. So the first one should come with factor -1. The second one should come with factor +1. the rest are zeros. And when we row by column, we will get this value. You see?
I see it.
Huh?
I see it.
Please raise hands who have doubts. Who doesn't do it? That's okay. That's
Believe you. I just-
Or who is not 100% convinced and wants more explanation. 1, 2. Who can explain? Take it and then just.
Okay.
Will I speak or show?
Okay, so for matrix multiplication, you take the row and you multiply it by the column. And then you get the individual answers based off of the different rows multiplied by the column. So this value should be the negative one here. So, and this one should be this one. So you can see in these terms that it's just x1 plus delta x, and it's just x1, which means that all of these 2 delta x, 3 delta x, and so on and so forth have to be 0 so that they don't exist in the final term.
Okay.
So
Yeah.
the negative one and positive one will, as the rows go down, they would shift one spot to the right.
So like the next row will be 0, -1, +1, 0, 0.
Yeah.
Yeah, okay, that does make sense.
Can you keep? Yes.
All right.
Yes. Yeah. Keep going now. Yeah. Many thanks. Please join me thanking Melody for tremendous help.
Thank you.
So
Definitely.
this is the main part of the code as it is programmed, in here. But lines from 106 to 115 do more precise way to program the same idea. So right now we program derivative as a summation of only contribution of 2 elements close to diagonal. If one wants to achieve a superb precision, one would have a little non-zero fractions outside of the diagonal. And the equation here tell how to do it. In the given time frame, there is no way to present it, but it's maybe another 5 minutes, but I will better do it another time when we all are fresh and relaxed. And I think we performed really well. Then the rest of the questions can be squeezed in the remaining meeting on next one. So just if time allows, think about what we did today. Try and compare to what you have to present, so that it will be not surprise next time. But what is our camera?
That one.
So meeting is done. Yeah. Many thanks for your dedication to the class.
Just tell me how many time measured in atomic units,
Delta,
right?
Delta, yes,
Yeah,
yes,
so-
okay.
Okay, and H, AM is energy,
Is operator of energy.
energy, operative energy, that's
Yes.
all. The AM,
Hamiltonian. You know, like when you tell AM, it sounds like someone is playing guitar and making the sure.
okay,
Not playing guitar, like AM.
Yeah.
So. I didn't want, sorry, cut to that, I didn't. Oh,
All right, convince me not to join 10 Club.
What? Or you don't- You don't want to.
What's happening?
So I'm not really sure yet, but some of the things that we will eventually do is that we put on like science type demonstrations for like school age kids. Typically we put together like. Yeah. he's gonna-
No, that actually sounds, I would actually be down for this.
Yeah.
And typically we're able to. I would never.
Yeah, so the kids lab, which was really late, and I have realized that it was on Tuesday.
And the membership fees, if I want to,
If you don't,
if I want to join your club, it's actually,
You can be a co-advisor.
no, I want just to be a regular member.
yeah. you can- Yeah.
Oh, okay. All right.
Bye, Demetrius.
Have a good night. See you Friday. My God,
Oh, sorry, Fred.
watch where you're going.